Hello, my name is Peter Liu, and I'll be telling you about work with Sam Kin and Maren Solicic at MIT on extracting interpretable physical parameters from spatial-temporal systems using unsupervised learning. For more details, please see our paper on arXiv. In this work, we aim to develop a method for analyzing datasets with spatial-temporal dynamics that are affected by uncontrolled variables. Our method is able to extract relevant hidden parameters that correspond to these uncontrolled variables and characterize the dynamics of the system. Previous works include direct sparse identification methods, which aim to explicitly determine the dynamical equations, and other unsupervised learning approaches that focus on discrete particle dynamics. We propose a method that uses a variational autoencoder architecture combined with a physics-informed encoder and decoder designed for spatial-temporal dynamics. The encoder extracts the relevant parameters while the decoder acts as a physics simulator and predicts the future propagation of the system. For more architecture details, please see our paper. We first test our method on a variety of simulated PDE systems. We also add around 10% noise to test robustness. After training, we can extract the learned parameters and compare them with the ground truth values. Shown here are the R-squared correlation coefficients from a linear fit. As you can see, our method accurately identifies and extracts the correct parameters without any prior knowledge about the governing dynamical equation. To test our method on a more realistic dataset, we use an ab initio solver to model a highly dispersive nonlinear optical fiber. After training, our method identifies 3 relevant parameters, 2 of which correspond to the group velocity and dispersion of the fiber. The third was initially unknown to us, but we were able to interpret it as a spurious phase velocity. In conclusion, we have successfully demonstrated an unsupervised learning method for extracting relevant and interpretable parameters from complex spatial-temporal datasets. All our code is available on GitHub at the link shown below. Finally, we would like to thank our funding sources for making this possible and our colleagues for useful discussions.